Yep, that's also an option as well. There are those help options upper right-hand corner. Some of the options are, ask my instructor, um, help me solve this, or view an example. You just want to keep an eye on how many, or how much, or how many problems that you're, using the help button for. If you find that you are using the help button for, almost all the problems on the problem set, then there might be some reviewing that you might want to do before, going in to tackle those problems. But um, yeah, yep. And like I said, you're always free to ask me questions as well. I'm happy to clarify, and that's what I live to do. So, all right, we are going to move on to section 1.6, where we'll be working on some application problems that involve linear and rational equations. Now, the first couple of examples are kind of warm-up examples. They come out of section 1.2, and even though they come out of section 1.2, they can be modeled with a linear equation. And the key to all this is, you want to end up creating an equation, in which case, you can solve for the variable. And in some cases, we might have an equation where there are two variables involved, and which could create some issues, because when you have one equation and two variables, you're not really sure, what to do in terms of isolating. Which variable do I isolate? And once you isolate it, you still don't get, a numeric answer. Um, so, you know, there's going to be information within each one of the problems where, they state a relationship between, two variables if you decide to define them. But all in all, what we want to do is take, information that's provided to us, and see if we can translate it into the language of math, i.e. variables in an equation, relate the information together so that we can come up with what they're interested in. So long story short, we're going to be tackling some story problems, which I know can raise a little bit of anxiety. I've definitely been there, done that, but I'm here with you guys every step of the way, and I've got some tips and tricks to help us work through them and hopefully make them go by as smooth as possible. All right. So let's start with applications of linear equations. And these are going to be application problems that, as you might guess, can be modeled by using a linear equation. In some cases, you might be able to define two equations using two different variables, in which case you're working with something called a system of linear equations. But there's a way to kind of bypass that as long as we relate the variables together in an appropriate way. So we'll just see where the problem leads us. And let's start with our first example. It says a total of 23,000 is to be invested. Some are going to go into bonds, and some of the money is going to go into certificates of deposit. So right off the bat, they tell us indirectly that we have two different, types of investments that we're not really sure how much is going into one and how much is going into the other. Furthermore, it says if the amount invested in bonds is to exceed that in CDs by 8,000, big money question here, how much will be invested in each type? So there's a lot of information to unpack here. Let's start by going back to the first sentence. Here it says we have a total of 23,000. That's to be invested. And how it's being invested is that it's, going across two different types of these investments. Some in bonds, which it doesn't tell us how much, and some in certificates of deposit, in which, and again, they don't tell us how much for this type. They do give us a special relationship between the amount in bonds and CDs, though. It says the amount invested in bonds is to exceed that in CDs by 8,000. Now that word exceed is kind of key for us. It means that, this amount is more than that in CDs. So we could associate that with the operation of addition. Now, speaking of operations, going back to a total of 23,000, okay, if we wanted to fold that into an equation, we'd have to set something equal to 23,000. And what are we setting equal to 23,000? Well, it would be the sum of how much goes into bonds and how much goes into certificates of deposit. So everything making sense so far, folks? Now, notice that we don't have the amount in bonds specified or the amount in CD specified. These are opportunities for variables. So we get to choose which variables we want to use since they don't force any upon us. And you want to use variables that will help the problem make more sense to you. So if you want, you could use X and Y, or we could use B and C, whichever you feel more comfortable with. If it's all right, I'm going to use B and C. And I'm just going to indicate off to the side that the amount in bonds is going to be given by the variable B, and the amount in CDs given by the variable C. And I also want to reference back to the idea that the 23,000 is split across the B and the C, right? So I want to make a note that the amount in bonds plus the amount in CDs is equal to 23,000. Now we have variables for each of these. The amount in bonds is B, the amount in CDs is C. And eventually we get to a point to where we have an equation, but unfortunately this equation has two variables. It wouldn't be possible to pin down the specific values of B and C with this current version of the equation. So here's where the second part of this problem comes into play. We need to probably put into math this relationship that the amount in bonds is to exceed that in CDs by 8,000. Can anybody come up with an expression that would represent exceeds the amount in CDs by 8,000? Not B plus 8,000. How about C plus 8,000? Because it says the amount invested in bonds is to exceed that. No, but definitely a good shot there. Yep. So we can actually come up with an equation for B based on that relationship there. The amount in bonds is to exceed that in CDs by 8,000. So if we look at the amount in CDs, we would have to add 8,000 to it to get the amount that's in bonds. And the benefit of establishing that relationship is that we can replace the variable B with C plus 8,000. Now when we do that, I'll use parentheses because in some cases there might be a number in front. But upon replacing B with C plus 8,000, we have an equation where there's only one variable, and this is something that's going to be solvable because of that. We can remove the parentheses. And it's really just business as usual. This is really a linear equation, and we're using c's instead of x, but the approach would be the same, right? On the left-hand side, you can combine the c's to get 2c plus 8,000. Subtract 8,000 from each side to get 2c is equal to 15,000. What we would do next is divide by 2. And that gives us 7,500. Do you guys have any questions about the equation, how it was formed, or anything leading up to this point? Now, do keep in mind that the 7,500 or 7,500 is for the amount that's in CDs. Okay, so I'd like to make a note that this is for the amount in CDs. Would we be able to figure out how much is in bonds based on this dollar amount that's in CDs? For sure. Yeah, what would we do to 7,500? Yep, you could plug it into our equation for B. You could also subtract it from 23,000. I'm going to go the first route, where if we plugged this in for, or plugged it into the equation for B, we'd have to add 8,000 to it, and we would get 15,500. Okay, so the amount in CDs would be 7,500, and the amount in bonds would be 15,500. Okay. Now clearly, the amount in bonds is 8,000 more than 7,500, because that's how we constructed it, right? But to further verify your answer, you could check that the sum of these two values is equal to 23,000. Okay, and then if you type these into the calculator and add them together, you do end up getting 23,000 as their sum, which helps to further verify our answers of 7,500 and 15,500. All right, do you guys have any questions about that? That wasn't that bad, was it? Okay. Well, let's try another one before we get to a problem that's officially out of section 1.6. A little different context here. A builder of tract homes reduced the price of a model by 10%. If the new price is $405,000, what was the original price? Then to follow that up, how much can be saved by purchasing the model? All right, just a quick heads up. This is for that follow-up question. It's from the perspective of a purchaser. All right. So let's start with the first sentence here. There's a reduced price. Now, reduced can be associated with the operation of subtraction. And how much is it being reduced by? Well, that's based on the original price. We're reducing it by 10%. Okay, so let's maybe make a note that that's based on original price. It says here that the new price is $405,000. So that's after we've taken 10% off the original price. That's the value that we would get. And of course, the big money question is, what is the original price? So we want to figure out the original price. It's not provided to us, obviously. And since it's a quantity that's not provided, that's maybe an opportunity for a variable. And would you guys be okay if I used the variable P to represent the original price? If so, I want to make a little note here that the original price is given by P. We could make a little statement about the new price. The new price is 405,000. Now, how are we going to relate these two? Well, we could start with the original price P, and bearing in mind that we're reducing the original price by 10%, what we could do with this P is subtract 10% of it. Now, in these application problems, when percentages are provided to you, it's best to convert them to their decimal format. And in this case, rather than using 10, we're going to want to use 0.10 instead. Now, we're going to subtract off 10% of the original price. So an expression for that would be 0.10p. And upon subtracting 10% in this way, we should end up with the value of 405,000. Does all that make sense? All right. So here's how we can relate, those two quantities. And now the algebra kicks in. All right. On the left-hand side, we technically have like terms, and we can combine them as such. And something that might be helpful is just noting that the coefficient of the very first p there is a 1. And keep in mind how we combine like terms. We do so by combining the coefficients. So essentially, the new coefficient of p is going to result from 1 minus 0.10, which is 0.90 times p equals 405,000. Now, 0.90p, just want to make a comment about that. If you're purchasing a tract home that was reduced by 10% of the original price, then effectively you're paying 90% of the original price. And we can see that, by virtue of our algebra, we see 0.90p equals 405,000. So from a conceptual standpoint, hopefully, this term on the left-hand side makes a little bit of sense. But, back to the algebra here. To isolate p, we would divide each side by 0.90. And we would get a p-value, or original price value, of 450,000. Confirmation on that from anybody? Cool. So that would be the original price. And that answers the first question. But keep in mind, they want to know how much can be saved by purchasing the model. So right underneath this, I'll indicate my workspace for how much is saved. And basically, it's going to be the difference of the original price and the new price. Okay, so I'll write that out. And we just figured out the original price was $450,000. And the new price was provided to us as $405,000. And the difference between these two quantities is $45,000. So by reducing the original price by 10%, the seller is knocking off $45,000. And so the purchaser, I guess theoretically, would be saving that much because he's now he or she is purchasing it at 90% of the original cost. So that's quite a deal in my opinion. But anyway, questions, comments, concerns about anything we've done so far? I know the hardest part of these application problems is really just setting up the equation. So I hope I'm doing a good job explaining how to do that, because to me that's the most important thing that I can help teach you guys. So you guys doing good? All right. Thank you for the feedback there. So we're now going to get to two different types of applications that officially come from section 1.6. I'll let you know that there are more types of applications in section 1.6, but I'm really just going to be focusing on the ones that I think more directly relate to our course description. The other types of applications would include mixture type problems and those distance equals rate times time problems. So I'm foregoing those. That's not to say we won't encounter those types later on in the course, but for now I just want to kind of keep the focus on the simple interest problems from that section, as well as something called a constant rate job. So have we heard of simple interest before? Just want to put my feelers out there. All right, cool. If you haven't, simple interest is, in simple terms, a fee that is paid for borrowing money. All right, and it's a two-way street. All right, you can borrow money from a lender. All right, in which case, there's going to be a fee usually associated with that, or you can invest some money into, an investment firm. In which case, for giving them your money, you can earn some additional monies. It's kind of like a fee that they pay. But there are lots of different ways of calculating that fee. One type is known as simple interest. And the way simple interest works is that it's based on how much is being borrowed initially, an interest rate, which is a factor that is used to calculate how much extra would be owed, and then the total time that the amount is the money is borrowed for, and usually that's in years. So for example, I took a loan out to finance one of my cars, and I had 5 years to pay that back, and they charged simple interest. And how they did that was they used the amount that I borrowed from them, did my credit history and everything like that to have the computer spit out an interest rate, and then multiplied those two values with the total time that I had to pay back the loan, which was 5 years. There's another type of interest called compound interest, where there are calculations going on within each year throughout the duration of the loan. But we'll look at that one later. Now, there is a pretty easy formula which helps us calculate that fee, or that additional money that is owed on top of what's borrowed. And the formula goes like this: capital I, standing for interest, is equal to P, which is the initial amount of money borrowed or loaned, often referred to as the principal, times capital R, which is the interest rate, times T, which is the time in years. And so if you multiply all three of these out, you can figure out how much money is owed, at the end of the loan on top of the original amount borrowed. There's going to be an application problem coming up where it's going to be in the context of an investment. And by that, we're looking at Betsy, who looks like she's a recent retiree, that would like to earn an additional $5,000 per year in income. She has $60,000 to invest and can invest in bonds, which have a rate of 13% per year, or CDs, which have a rate of 3% per year in this problem. How much money should be invested in each to get this $5,000 in interest per year? Well, what they want you to assume is that this $5,000 is being generated by interest coming from two different accounts: the account that involves the bonds and the account that involves the CDs. And so she's investing across two different types of accounts. She walks in with $60,000. They don't tell us how much of that $60,000 is being applied to bonds nor the CDs. So that's kind of a clue as to how we'll define our variables. But by the end of 1 year, the interest that she's going to earn from bonds added to the interest from the CDs should total $5,000. All right, so this $5,000, I just want to make a note that this is going to be the total interest. Now she walks in with $60,000, and this $60,000, I want to know, is split across bonds and CDs. We have a couple of rates here: 13%, that's for bonds, and 3%, which is for CDs. It doesn't tell you explicitly, but they just want you to assume, a 1 year time period in order to earn this $5,000. Now, with all that said, I find that making a table for a problem such as this is super helpful. It helps us figure out, what represents the principal, rate, and time, helps us construct expressions for the interest, and it just keeps it all nice and organized, which is always a good thing when solving application problems. So I'm going to make a table that has 3 rows and 5 columns. All right, so if you want to follow along with me in making that, that'd be awesome. This first column is going to be designated for the type of investment. One type is the bonds. The other type is the CDs. CDs dollars going into that account. The next column is going to represent the principal going into each account, which we'll decide on that in just a moment. The next column is going to be for the 2 different rates, which those are provided for us. The following column will be for time, which, as I mentioned, even though it doesn't state it explicitly, they just want us to consider 1 year. So I'm going to just quickly put ones in to each of those slots. And then the very last column is going to be for the interest. which I want to remind us is principal times rate times time. Now it doesn't tell us how much is going into the bonds. So with regard to the principal and bonds, let's just call that X. It doesn't tell us how much is going into CDs, which if we wanted to, we could use a variable Y, or we can write an expression that involves this X. If X dollars are going into bonds, then the amount that's left over to go into CDs would be 60,000 minus X. So in other words, the difference between 60,000 and how much you put into bonds, that's how much is going to go into CDs. That make sense? Sweet. Now for the rates, we have 13%. That's for bonds. Let's use 0.13 instead though. And then we have 3%, which is for CDs. Let's write that as 0.03. Now because both principles involve the variable X, the interest formula is going to kick out an expression involving X. Now to get the interest expressions, those result from multiplying P, R, and T in each of these rows. And when you multiply P, R, and T in the first row, it simplifies as 0.13x. When you multiply P, R, and T in the second row, because the P has two terms involved, it's best to write this as 0.03 times the quantity, 60,000 minus X. Okay? Now this is how we're going to create an equation. We want to keep in mind that the total interest is 5,000, and we're going to get interest from both the bonds and the CDs. In fact, we have expressions for the interest, 0.13x and 0.03 times this quantity. What that means is that if we add these two expressions together, their sum is going to equal 5,000. And that connection between the interest of 5,000 and these two expressions is what helps us get an equation going. The equation would go as follows: 0.13x plus 0.03 times 60,000 minus x equals 5,000. Okay, so in other words, the interest from bonds plus the interest from CDs equals 5,000, and that's exactly how we get this equation. So I'm going to give you the next couple minutes to solve this equation. Keep in mind that your answer is for bonds, okay, and you can use your answer to get the amount that's in CDs. All right, so after a couple minutes or so, I'll jump back in and we'll look at the results. We'll take a break and then wrap up the rest of this section afterwards. Okay, so go ahead and see if you can solve for the amount in bonds and then afterwards the amount in CDs. Okay, here comes the big reveal, folks. All right, so I distributed the 0.03. Going to combine like terms now on the left. 0.10x plus 1800 equals 5000. Subtract 1800 from each side to get 0.10x equals 3200. Divide each side by 0.10. And how do you feel about x equals 32,000? Rock on. So keep in mind that this is the amount that is in bonds because we defined our principal for bonds using the variable x. It does want to know how much is in each account. So what we could do is keep in mind that the amount in CDs is given by the expression 60,000 minus x. So now that we have a value for x, we could do 60,000 minus 32,000. That's going to give us 28,000. And this is how much would go in the CDs. So at long last, we have both dollar amounts. Now, you could check this, first of all, by adding the two together. The sum should give you 60,000. But you could also use the formula for simple interest to calculate the interest that you would get from the 32,000 as well as the 28,000. And whatever two numbers you get, those should add up to 5,000. Okay? So just a couple of ways that you could check this. It's about time for a break though, but before we go on that, you guys have questions about this problem? All right, folks, let's go ahead and wrap up section 1.6 with the last type of application problem I'd like to spotlight from that section. It's known as the constant rate job. And as you'll see, a constant rate job can be modeled by using a rational equation. And the reason for that is because of a formula that I'll be presenting to you folks in just a second. So applications that involve these constant rate jobs will typically lend themselves to rational equations. And let me just spill a little bit of the details on what a constant rate job is. They're essentially jobs that are completed at a constant rate. So it seems kind of like cyclic reasoning there. But basically what this means is that there's no slowing down or speeding up or taking breaks when a job is being done. All right, so from point A to point B, everybody's working at the same speed. Nobody's slacking or trying to get ahead of anybody else, and there are no breaks. And that's kind of a key concept to know beforehand, because it's actually what helps form the basis of this constant rate job formula. So before I get to the formula, I do want to just kind of create a toy example here using one of my kids' favorite pizzas, Little Caesar Hot and Ready. I'm going to sketch out as best as I can, an illustrated hot and ready pizza, which usually come, cut into 8 slices. Look at that awesome artwork there, right? And of course, all the slices are not very uniform. And we like to call it hot or ready because, when you pick it up, it's either steaming hot and it burns your mouth, or it's just kind of like lukewarm and then all the cheese is solidified. And so, that's a case where it's ready. It's not necessarily hot. But anyway, I want to have us assume the following info. Let's assume that it takes 8 minutes to eat the whole pizza. Which, back in my wrestling days, this was totally possible. I have a question. How much is eaten after 1 minute? Okay, so let's assume that somebody's eating a hot and ready pizza or hot or ready pizza, and they're eating at the same pace throughout an 8-minute period, in which case after 8 minutes is up, the whole pizza's gone. All right, so there's no speeding up, slowing down, no taking a few minutes out to watch some TikTok or anything like that. So from start to finish, it takes 8 minutes. How much of this pizza is eaten after only 1 minute? Any guesses? One slice. Yeah, exactly. So if this thing is cut into 8 slices, then after 1 minute, an additional slice is eaten. Okay, so let's say, starting out and, we're under the assumption it takes 8 minutes to finish the whole thing. Then after the very first minute of eating this pizza, 1 slice is gone. Now we could represent that 1 slice as a part to the entire pizza or as a fraction, okay, part to a whole. In particular, that slice right there would represent 1/8 of the pizza. If we're under the assumption that a job is being completed at a constant rate, there's always going to be a connection between the total time it takes to do the job and the amount of the job done after 1 unit of time. So you can see that 8 minutes eventually led to an answer of 1/8. And 1/8 is the reciprocal of 8. And that's the key. In this box here, it says if a job can be completed in X units of time, then the amount of the job done in 1 unit of time is going to be given by this expression, 1/X. Okay, where X represents the total time. Long story short, in a constant rate job problem, if we're provided a time value, a total time value that is, then we can quickly jump to the amount that's done after 1 unit of time just by reciprocating it. So that takes us to our last example. Clarissa and Shauna, working together, can paint the exterior of a house in 6 days. So that's the job, painting the exterior of a house. Shauna by herself can complete this job in 5 days less than Clarissa. How long will it take Shauna to complete the job by herself? This is another type of problem where I think making a table will definitely benefit us. So let's maybe construct one together. This is going to be a table that has 4 rows and 3 columns, just to give you a heads up. That perfectly square table right there, huh? But anyway, I'm going to title the columns. The first column is going to focus on which person. Okay, it's going to focus on the people, that are part of the problem. The second column is going to be for any time values that we can get out of there, and then the last column is going to be representing the amount done after 1 unit of time. And basically, what we'll do is we'll take any time amounts that we can construct and reciprocate them to get the fractions that will be populating this last column. The first person I'm going to put here is Clarissa and Shauna. And I'd also like to consider them when they work together. In fact, in this first sentence of the problem, it says Clarissa and Shauna working together can paint the exterior of the house in 6 days. So that actually gives us something that we can put in the very last row. In the time column, working together, it takes them 6 days. So I'm going to put 6 there. So what would that mean about the amount of the job done after just 1 day? What would that be? I'll keep in mind our constant rate job formula. Okay, so 1/6, yep. So maybe this might help. We'll put x above time and 1/x above the amount. Now it doesn't state explicitly how many days it takes each one of the people to do it individually. It instead gives a connection between the two time amounts. It says Shauna by herself can complete this job in 5 days less than Clarissa. So this statement is actually basing Shauna's time on Clarissa's, which they don't really tell us how long it takes Clarissa to do it either. So what I would do is I would maybe assign Clarissa a time value of x, which of course is going to mean that the amount done after 1 day is 1/x. What could we put for Shauna's time amount? Well, keep in mind it's x minus 5, yep. Right here it says 5 days less than Clarissa. So what that means is that the amount done after 1 day by Shauna would be given by the expression 1/x minus 5. Is this all making sense so far? Okay. Here's how we're going to create an equation. I'm going to write out this subtle but important fact. Clarissa is going to contribute a portion of the 1/6. Shauna is going to contribute a portion of the 1/6 as well. And so what I'm doing is I'm focusing on when they're working together. Okay, so let's think about when they're working together. If we take the amount done by Clarissa and add it to the amount done by Shauna, okay, so we're assuming they're working together. Each of these two people are going to contribute to the 1/6 that's completed when they're working together. So that actually allows us to get an equation involving the expressions in the last column, namely 1 over x, because that's the part of the job done by Clarissa after 1 unit of time. And then Shauna's contribution to this 1/6 is 1 over x minus 5. So long story short, once you have your last column filled out, what you do is you take the fractions for the individuals, you add them together, and you set it equal to whatever this expression is. So it's basically, we're assuming that the 1/6 is split up into 1 over x and 1 over x minus 5. And in making that connection, we end up with a rational equation. Okay, before we go to solve it, do you guys have any questions about how it was set up? All right, so let's be in the mindset of how to solve a rational equation, something we were discussing last week. What you want to do for a rational equation is multiply each part by an LCM. That's going to cancel out all three of these denominators once we've simplified. Now the LCM to use is going to be 6x times the quantity x minus 5. And what we'll do with that is we'll put it in front of all three fractions, we'll simplify, and then see what kind of equation that we get. Do you guys want to take a moment to simplify that? Go ahead and simplify that, and I'll jump in just a second so we can check our answers. All right. So the x's cancel out here, leaving behind 6x minus 5 and 1. I'm going to write that as 6 times quantity x minus 5 plus the x minus 5's cancel, leaving behind 6x times 1. I'm going to write that as 6x. And on the right-hand side, the 6's cancel out, leaving behind x times x minus 5 times 1. So hopefully that's what you got when you simplified. And we're going to go a little bit further and clear parentheses to get 6x minus 30 plus 6x on the left, x squared minus 5x on the right. And upon canceling out all these denominators and clearing parentheses, we end up with a quadratic equation. And that's because the highest power on x now is a 2. So what I would do from here is try to set this quadratic equation to 0 by moving some things over to the right-hand side, because if the expression we get after we simplify factors, that's going to be our quickest way of solving for x. So let's do this first, though. Let's combine the two 6x's on the left to get 12x minus 30 equals x squared minus 5x. And then we can subtract 12x from each side, as well as add 30. These cancel. We do get 0 on the left, and on the right, we'll have x squared minus 17x plus 30. So to see if it factors, we'd want to come up with numbers that multiply to give us negative 30, but also add up to negative 17. Any recommendations as to what two numbers are going to work for us there? Yep, we could do x minus 2 times x minus 15. Now, when we have one side completely factored, set equal to 0, you may recall that we set each factor to 0 to solve for x, and that's what we'll do here. And we get a couple of answers, x equals 2 and x equals 15. Now, there's actually an issue with one of these values of x. Anybody know what value of x might, cause the issue? $15? All right, so why do you think 15 might cause a problem for us? I would actually consider the 2, because if you look at our table, using x equals 2 as an answer will make Shauna's time negative 3, so she would complete the job in negative 3 days. And I think it's obvious as to why, we probably wouldn't want to use 2. So nice try, though. I'm going to cross that out because it doesn't have any meaning in this setting. So we should probably opt to use the 15 then. But keep in mind what 15 designates. This designates Clarissa's time. Did it ask for Clarissa's time, or did it ask for Shauna's? It actually asked for Shauna, right? How could we figure out Shauna's time now that we know Clarissa's time? You got it. Yep. 15 minus 5, because Shauna completes it in 5 days less, in which case we get 10 days as Shauna's time. And that's the official answer to this problem. And it was all based upon figuring out Clarissa's time first. All right, but once we do all the grunt work for that, it's a real simple matter of just subtracting 5 from the appropriate value of x, and we get Shauna's time.